I was muted. Okay, that's why the sound is not working, I guess. Okay. Good that I was talking all the time. Nevertheless, isn't the first stream that I spent talking. Yeah, okay, so now it's working. Nice. Okay, cool. So, let's go. Lasergurkenland, can we get that? Can we get that? And like this. Awesome. So, Lasergurkenland is a Anarchy server, so you are allowed to... Oh, do I have to dupe something in this episode? I think I have to. Anyway, so this is a server where there are no admins, there are no rules and no plugins. So yeah, it's a vanilla environment. I'm already like going back. I was advertising all the time with how pure vanilla it is. It is actually a pure vanilla server, but the performance of pure vanilla is just unacceptable when you reach more players, which would be nice to have more players online here. So I might have to switch to paper speaker, so that's that. But currently it's pure vanilla. It will always stay yeah, vanilla-like. If there's anything else I can do that trades in performance and otherwise it's unplayable, I might have to switch to an unofficial server binaries that improve performance. But yeah, the gameplay should be vanilla. So that's that. Okay. Right. Yes. So please join. It's paid in advance for multiple years already, so the server won't go away randomly. And yeah, it's free to join and so on. There are no word resets. I have a lot of disk space. Well, I have to admit that we lost some data lately due to an attempt to switch to Spigot. I think it failed on like moving the huge nether world files because they are in a different location in vanilla and bucket. But oh, I got a call. Oh my gosh. Okay, I have to quickly go AFK. You know, these business calls, gotta do them. All right. So since I was muted, oh, we have people online. Okay, since I was mute, why did I have damage? I don't know what exactly you know already. Let's just skip the advertisement part and the whatever part. For news about like data loss and so on, check out zillion.com/lasergurkenland with a capital L, or just zillion.com and click through to Lasergurkenland on the interwebs with your browser for information and stuff like that. Alright, anyways, so we are going, we reached the 1000 border. We are going to watch a Rust talk today. Probably not the full one because it's over 4 hours. It's from our friend Jon, who likes to publish Creative Commons Rust content, which is, in my opinion, a bit advanced, and I would prefer something more basic. But if you search for something more basic, they usually just explain what an if statement is, and that might be too basic. So yeah, that's that. Anyways, Jon it is. The title of the video that I'm now going to play back is The What and the How of Futures and Async Await in Rust. It has 40,000 views, currently is uploaded in 2018, and it's from Jon's channel. I can't pronounce his full channel name. Check out the description for full credits and link to the original video. Anyways, so yeah, I guess this has to be a duping episode, so it might be a little bit annoying for me to get everything set up and stuff. But let's get right into the video, and I try to get my stuff back. Okay, cool. So can I press that button and then that button, and then I can go like this.
Everyone, welcome back. This is a stream that people have been asking for a while. We're going to tackle sort of the whole idea of futures and asynchrony in Rust. And this, we're not so much going to talk about how you use it, but rather sort of how does it work internally in the language? What are the libraries like? How do they function? How do all the pieces fit together? So the goal isn't so much necessarily that you're going to like write lots of futures yourself, although you might end up doing that. And it's not really about writing async await code. It's just like, how are these components written in the first place? And so what we're going to do is we're going to look at futures first. We're going to start looking at Future 0.1, so the version that's sort of released and the ecosystem at large is using. Then we'll go into Tokyo, which is sort of one of the main executors for futures in Rustland today, and which deals with things like I/O, so input-output, like network connections, file systems, those kind of things. Then we'll look at the move to take futures and move it into the standard library, and what that looks like, how it differs from the existing future stuff, and why it's different. Pinning. So then you'll see that the new future stuff has the notion of pinning, and we'll talk about what that is and why that is. And then that ties in very strongly to the idea of adding async and await, the async and await keywords to Rust. So we'll talk a little bit about what those mean, how that works under the hood, how that ties back to pin and the future stuff in the standard library. This stream, I've mentioned this a little bit before, but this stream is going to be more sort of me talking about how stuff works. We'll probably look at a little bit of code. We'll do some reading of RFCs. It will also be some like drawing and diagrams and that kind of stuff. There'll be relatively little coding on my part, although if it's necessary, we'll do it. But this is really more of a goal or the goal here is more to sort of go through all the stuff, how it works, and explain it, because I haven't really found any good cohesive explanations that cover the entire ecosystem and where it's going, and so the hope is that this might do that. If you have any questions as we go, feel free to fire them off in chat. I'm monitoring that on the side, because if you have a question, chances are someone else who's watching either now or later will also have the same question. So questions are awesome. Just before we start, I'm Jon. I do a bunch of these live streams, and they're usually about things and we're building stuff in the Rust ecosystem. I've done a stream on open source contributions in Rust. We've done several where we've implemented various asynchronous primitives. We did one on asynchronous SSH. we've done a couple on implementing the Zookeeper protocol in Tokyo, and a bunch of other stuff that we've written. You can go back and look at my YouTube channel for recordings of all the streams. I also built a tool the other day. There's the video for building that tool is also online. That is basically a website where people can vote for what ideas they want to see next. So usually what I've been doing is on my, I guess I should, this is my Twitter account. If you want to follow me, if that's unhelpful, this one. This is my Twitter. Feel free to sort of follow that if you want to hear updates both about the stream, about Rust in general, and I tweet about other stuff as well, which may or may not annoy you, who knows. But I try to keep it relatively high signal. So usually what I've done in the past when trying to decide what streams to do and what I did for this stream as well and how this came to be is basically to sort of tweet out polls or just asking people, what would you like to see? And this particular stream came about because over basically the past year, I've had a lot of people say, can you just like cover how async works? And in particular, I sat down with Brian Myers, who I met through Twitter actually, and through the stream in New York the other day, and he said, how about you just do one on futures in Tokyo? Just explain how it all works. And I was like, that seems like a great idea. But I wanted a better mechanism for learning what things all of you want to watch. And so what we built the other day was this tool where I put in ideas for upcoming streams, and you can vote on them. So in this case, there are 4 IDs here currently, and it uses ranked choice voting, which is cool. You should look that up if you don't know how it works. The basic idea is that you can sort of rank your candidates, and over time, it runs elections to try to figure out what is the most preferred candidate stream. And then what I'll do is, over time, I will just take whatever is currently winning, and then I will do that stream, and then remove that and run another election. It's pretty neat. You can catch the stream that I did if you care. It's not written to be any kind of secure. It's broken in all sorts of security ways, so like, don't abuse it. It's just there for you to be able to express what you would like to see. All right, all of that said, sorry, this just, sorry, give me 1 second. That's not what I wanted to happen. I just lost the chat, which is annoying. Like so. There we go, chat back. All right, so let's dig into futures. For those of you who sort of don't know what futures are at all, I won't go through sort of the entire story, but I will give you some basic background on futures and asynchrony in Rust, or in general for that matter. The idea behind futures is that we want some way to express a value that is not yet ready. So if you come from other languages, this is similar to JavaScript promises, and many other languages have a similar kind of concept of a value that's not quite ready, but you can do, if you just wait a second or wait a little while, then the computation's value will be ready. You could think of this either as something that's compute heavy, like I need to compute a bunch of hashes and then eventually the hash is ready for you, or you can think of this in terms of asynchronous I/O, like you have a network channel and you want to try to read from it, but there's nothing currently on the channel. And so what you get back is a future that says, eventually there's going to be some stuff for you. At a very high level, you can think of this as a building block for doing lots of concurrent operations. So the idea is you have an asynchronous computation, so you have something like, I'm sort of reading from a network connection, I'm just not going to block the thread right now. The way this often comes up is, imagine you have a web server of some kind where you have, say, thousands of connections. You could spin up 1,000 threads and have each one sort of re-block and read on its own connection, but that seems sort of unnecessary. Like, why are we doing that? Why do we need all these threads? Instead, what you can do with futures is you can have one future for every connection, and then you have a single thread or some set of threads that are sort of just looking at all of them and just handling whichever one is ready at the time. If you come from the JavaScript world, or even for that matter, to some extent from Go, but certainly in the JavaScript world, you have this notion of an event loop. So you can think of your program as basically being single-threaded. And there's just one thread that whenever you tell it to like read from a network socket or something, it's going to just remember that you asked it to do that. And then when the network socket is ready, it's going to tell the thread, or it's going to sort of go, oh, that's ready now, and then run the computation. The way this often looks is, so the way this often works is you have something like, so let's see, I'm connecting to some server. But this is not going to be real code, but just take it for what it is. So imagine that I'm connecting to server 1 and server 2, right? So, and then I'm going to do like x.write foobar, and I'm going to do y.write foobar. And then I'm going to do x.read, and bar foo. I don't know what these services do. It's not important. So think of a program like this where I have a single thread, I want to connect to both, write to both, and read from both, right? Now, I could have this code just work this way, and sort of you're going to connect, and then you're going to wait until the connection has finished succeeding. Then I'm going to connect again, wait until that connection is finished. Then I'm going to write to X and wait until all of those writes are finished. Then I'm going to write to Y, wait until those are finished. Then I'm going to read, or then I'm going to wait until X responds to me. And then I'm going to wait until Y responds to me. This works, right? This is totally fine. But it's a little bit finicky because we're doing a lot of this waiting. So for example, why are we waiting for the stuff in foobar to be written to X? Like why are we waiting for all of that to go out to the network before we send anything to Y? Why not sort of send to X and to Y and then wait for X and Y sort of in parallel? And whichever comes back first, we're going to deal with first. And so in a futures-based world, what you would generally write is something along these lines. And then, so this gives you back a connection, and what we're going to do is we're going to write foobar on that connection. And then, again, all of this is, the types here are all made up. Like, think of this more as trying to explain the idea behind asynchronous computation. So here we get back the connection, reduce.read, and here, whenever we get the bytes back from that, so let's say this returns the connection and the bytes that we read, then we check that the bytes are barfoo, right? And here we don't even need X anymore, right? And then we do the same for Y. They basically do the same thing, so the two features are going to look the same, right? This is going to give you back a future, and this is also going to give you back a future. If you tried to like print this future or something, if you tried to figure out what it was, it would just tell you, I don't know yet, right? This doesn't, it's not like, I guess here, let's make this just be a Boolean, right? So this entire thing evaluates to a Boolean, and this evaluates to a Boolean, right? So if you were to look at this future, immediately sort of on this line, we would do something like print line, like the future. If we were to do this, this would not print true or false, right? What this would print is, this is a thing that will eventually become a Boolean. And so that's what we mean by asynchronous computation of futures. Similarly here, the type of this is also, this is something that will eventually become a Boolean. And then where this gets interesting is now you have these two things that are basically just descriptions of what to do. You can think of this code as, this code hasn't done anything yet. It's sort of lazy. It's not quite true, but you can think of it as, it hasn't done all of the computation yet. It's just describing the steps that it's going to go through, right? This is really just saying that whenever this finishes, do this, and whenever that finishes, do this, and whenever that finishes, do this. But none of the things have finished yet. They might not even have started yet. And so this is where the notion of an executor comes in. So an executor is basically something that you can give futures to, and it will just make sure that they get done. So if you have an executor, so let's say X is an executor. I guess I should say A is an executor, right? Of some kind. We don't really know what executor is yet. then you can think of something like you're going to do a dot run. I guess we should call these fut x and fut y.
The fuck?
So we can sort of run fut x, and we can run fut y, and only when we run them are we going to get back the x. That's this, right? But this still is sort of weird. This is saying run the entire x future and then run the entire y future. That doesn't seem very much better than what we had initially. And so what we might want to do is something like, in this case, because we might not even care about the return values. In fact, maybe we want the assert back here. Maybe what we really want is to say, just run those and have them happen. I don't care about the return value. That's when you can use the idea of a spawn. So here we would do, so fut x, and then, sure, we'll inspect this better, but let's use and then for simplicity. So this maps to a Boolean of whether it was equal, and we assert that it was equal. And then we do the same for y. Right? And so what spawn does is sort of tell this, tell the executor, just run this thing and make sure it gets run at some point, and do the same for y, and then we're, at the end, just sort of gonna, like, block on all. Let's say that that's what it's called, right? So what this is saying to the executor is, just have these things run in the background, and I don't care what order they finish in, I just want them to be run at some point, and just tell me when they're both done. So you might wonder, well, how does any of this help, right? We've spawned these, but without knowing what that executor does, who knows? Like, how do we know they're running in parallel? And so this is where the whole idea of futures come from. And we're going to start looking now at the futures trait, because that is where all the sort of magic comes from. So, there are a lot of associated methods. Let's just focus on these top 3 lines. So a future, and keep in mind both of these are futures, right? This is a future and this is a future. A future is a thing that has an item. So item is the value that it resolves to when it completes. In our case, that would be Boolean because this is a Boolean, and Boolean because this is a Boolean. Error, which sort of goes away later, but let's talk about error for now. So error in our case is the error value that each of these futures, each of these intermediate steps would give you. Stop blanking my screen. So you can think of this as like a TCP stream connect is basically going to give you back an IO error, right, if it fails. But in the futures world, what that really means is this future is either going to resolve into a Boolean or it's going to resolve into an IO error. So think of this as this could be a sequence of results where you use a question mark operator. So the error type just keeps getting propagated. So if you error, you don't execute any of the other and-thens below you. You just execute your current one, it fails, and then the future just resolves into whatever that error type is. So that's what type error here is. And then all of the magic for futures happens in the method poll. Let's zoom into that a little bit. So notice it has a pretty long docs, and that's because poll is very important in futures land. And let's look at what it does. So a poll, if you poll a future, it takes a mutable reference to self, so to the future itself, and then it gives you back a poll of the item and the error. Okay, so what is a poll? A poll is really just a result async of the type and the error. So what is an async? An async is either ready or not ready. And this is where we get to the heart of all of this. What the executor does, so what an executor does when it has a bunch of futures. So imagine that we have something like a struct executor. Executor. Think of it as sort of having a vector of futures, right? It's not actually what it stores, but let's just imagine that's what it is. And when you do block on all, again, none of this is how the actual code is written, but I think it helps for exposition. What the executor is going to do is it's going to poll on all of the futures, sort of, right? So what we're going to do is for f in self 0, this, we're going to call f.poll. And recall that f.poll, what poll really is saying here is there are three possible return values. It's error, or it is async not ready, or it's async ready. So if there's an error, then the future is going to resolve with that error, right? So if poll returns an error, then that future error, then we might want some way to text in the browser bigger, sure. Is that better? So poll is gonna, I guess we can match on it, might as well. So it can either return async ready, and that includes a t, right, which is the item value, so the thing the future resolves to. It can return okay async not ready, in which case we have to do something, and it can return error of some type E. Now imagine that we had some way of communicating back to whoever, sort of, in this case we have the future, right? So we don't really have anyone to tell about the results. But let's think about run. Let's try to write this in a way where the return value is useful. Let's imagine that you had run all. And we're going to change this to be, instead of this, it's going to be run all, fut x and fut y. I guess, sure, let's do that. Right. So that makes sort of sense. So we're going to have a run all method, and instead of storing this inside the executor, we're just going to have an executor, and then it's going to be given the futures to execute. Vec future. And it's going to return a vec of sort of the futures item. I know this isn't real types, but you can think of this like, I guess, results. Future item, future error. Now this assumes all the futures have the same items and the same error, but let's just imagine this is fine for now. So what this function is really doing is it's going to keep like a results vector for f. Okay, so now our goal is to return the results of every future that we're polling, right? We're gonna do that later. This future result, it returned ready, and so now we have a result. I guess we're gonna need something like later mean right? Okay, so in this case, the future result, it's basically telling us it's finished. So async ready means that the future said, I've done all the work, like I've done all the and-thens, and I have the result at the end. So the T here is the future item. So you can think of this as sort of like, we're going to store in results I, okay, T. Right? And then in not ready, what this means is the future is telling us I have to do more work. Right? There's a network packets I have to do, or I have to do some more computation. Come ask me later. And so in this case, we don't really have anything to do with this future. This still has to do more work. So we just sort of continue. If we get an error, then we stall that error in results. Right? So given this loop, we're going to be given a bunch of futures. We're going to call poll on all of them. And poll you can think of as sort of do more work is really what poll means. And then if it says I'm done, then we store the fact that it's done, whether that's an error or an okay. And if it turns not ready, then we have to basically call poll again, is what not ready means. And so in our case, what this means is we sort of need to do a loop here.
Isn't that so far how you would essentially write every threading code yourself, for example, in C or C++? Well, I mean, I didn't do that too much, but 2 times I did that, I wrote it like that. I had my loop and I was checking, are you done yet, and so on. Yeah, whatever. Okay.
Right? Because otherwise we would never call poll again. Right? Now, this is where you can see this start to sort of break down, like results isn't long enough to hold all these results, we would need to know when we finish, but the basic idea, I hope, makes a little bit of sense, that not ready just means we have to call poll again to make more progress towards yielding the item in the end, right? And so, I guess we can actually write this in a way where done is 0, something like this, capacity, futures, sure, let's do something even stupider. We're gonna not sort these in order. Again, I realize these are kind of silly, but you'll see why in a second. Just to make this like not be entirely stupid. Okay, so now what we're doing is if we get ready, then we push that result along with the future that was resolved this way, so the index. And I guess we do done equals 1, the same here, and then this loop is now while done not equal to futures.length. And then at the end, we're just going to return results. Right? So this means we're going to keep calling poll on every future until every future has returned async ready. Maybe cycle the iterator instead of the loop. So we need iter mute because poll takes a mute self. So otherwise we wouldn't have the mutable reference. Maybe cycle the iterator. Oh, so this is broken in all sorts of ways. But I don't, it's the wrapping around it is not super important. It's more that you understand the idea that we're gonna, if we're given a bunch of futures, we have to call poll on all of them. And then if any of them return not ready, we have to make sure to call poll on those futures again, right? Now, you might start to wonder, there are many things you should start to wonder when you see this code, like what happened? So here, this means that we're gonna poll a future after it has finished. Why? Here, this seems like it's just going to be a busy loop, right? We're going to call poll, it's going to tell us it's not ready, and then we're going to immediately call poll again. That seems relatively inefficient. And you're totally right on both counts. In fact, you're not allowed to write this code. If you wrote this, your implementation of an executor would be broken. In particular, we need to be
so far. so much to my comment that that's how I would write it and how I've been writing it all the time.
Us. And so the poll documentation is actually pretty decent. Notice that it says you want to query whether its values become available. We'll get back to this registering interest. It checks the internal state of the future and assesses whether the value is ready to be produced, which means basically has your computation finished or has it not? And notice that implementers of the function should ensure that it never blocks, right? And so you can sort of see this from this code. If poll block, then we're not going to poll any of the other futures for a long time, so they're not going to make progress either, right? So you can think of poll here as just making progress on whatever you're doing, whether that's sending network packets, receiving network packets, doing some more iterations of computing, like waiting for a timer to pass. So poll is just going to do a little bit of work and then continue. And this
what did I
should
collect?
lead you to realize
I
why
errors.
Calling run all on both future x and future y means that we're going to make it progress on both at the same time. So remember, this is all single threaded, but we now have a single thread that is going to sort of poke at the x future and say, are you ready yet? And the x future is going to say, I did some work, but I'm not ready yet. And we're going to poke at the y future.
What is happening with the
say,
sound?
Are you ready yet? It's going to say, not quite yet, but I did some work. And then we're going to keep alternating between
What is happening with the sound?
Until one of them finishes, and we're just going to poke at one until that.
There's an echo. Oh, the drugs kick in. Okay, so it's in the video. Let's go.
Finishes, and eventually they're both going to be done. And now a single thread has been doing sort of both of the pieces of work in parallel just by switching between them.
And this extends, of course, to doing many computation, right? So you can have a single thread that sort of manages, say, 1,000 connections. And all it's really doing is sort of checking all 1,000 of them, like, are any of you ready? And then one of them goes, yeah, I'm ready. And then it pulls on that to make some progress. And then it goes back. There's an echo. Ooh, the drugs just kicked in.
Oh, he also said that in the video.
Is there still an echo now? Or is it better? Like, is the echo now gone? This delay from speed to chat, it's pretty annoying. Still the same, huh? Interesting. And how about now? It randomly started in the middle of my sentence. That's so weird. So I just turned the microphone back off and on. Still. Huh. Well, that's weird. Shouldn't matter. And it's still there. Huh. How unhelpful.
Bro, fuck.
Now it's good. What? That is the weirdest thing. So now it's fine? It sounds weird now. A little better. Oh, I wonder. Does that help?
Oh yeah.
Like there's an internal echo. That like there was another microphone turned on. Is it now better? Fantastic. That's so weird. Why did that suddenly kick in now? Huh. Oh well. Okay, so you can see how this setup allows us to handle many computations. They're sort of like, if you imagine that you have a bunch of computations, and they're not really compute heavy, so they're not like taking up CPU cycles, but instead, all of the futures that you have are mostly waiting, like waiting for a network packet to either be able to be sent or to be received, or they're waiting for a timer, then they're all just sort of sitting there. And so this single thread has a lot of spare time.
Wow.
So if you have a 1,000 thread, one free connection,
Efficiency
most of your threads are just
at its
sitting
best.
there. Here, we have a single thread that what it's going to do is just make sure to work on whatever is ready and just keep all the other things in the background. And so this ties back to what we talked about with not ready, that when a future is not ready yet, so its final value is not there, then it returns not ready, right? But notice that here's where it gets interesting. In this situation, the future will also register interest of the current task in the value being produced. When the future is ready to make progress, it should unpark. Okay, so this park and unpark business seems important. You can think of this as, when I call poll, what you should do as the future is you should mark yourself as not ready by returning not ready, and then at some point in the future, you're gonna make someone mark you as ready again, right? So here, there's basically a contract where if you return not ready, you've arranged, there's now some noise in the background.
Yeah, that's me.
Sound is just the weirdest. I wonder if I can just do this instead. That might be better. How about this? Is that any better? Or is that worse and brings back the echo?
So many.
More what I want, but it's pretty unhelpful.
Well, I guess the question is which. This is that one, and this is that one.
Okay, great. Well, I guess we're back to this. I think this is the right setup. I don't know what the noise is. Worse. I just wish audio would work. So you're saying now it's terrible, or is it now fine again after I disabled this business? Like,
Oh, come
now
on.
you can hear me and it's fine, or now it's okay. Now it's good. Fine. Okay, so there's this contract in not ready that says if you return not ready, then you must have arranged for yourself to be woken up again when you can make progress. Right? So poll says I can't make progress. That's what, if not ready is returned, then that's what poll means. I can't make progress. But I've like told my friend over there to wake me up when I can make progress. The basic idea is like think of a future
my
that
good
is like
stuff.
waiting on a timer, right? So you ask it, hey, are you ready? And it goes, no, I'm not ready. My timer has expired yet. What that future is going to do is, let's imagine there's some other thread out there that's running, that's checking time. It's going to tell that other thread, hey, you other thread over there, can you wake me up when this time is reached? And so the way that works is there's this task notion. So where is the documentation for task out there? Futures. Task. Task current. Right, so you can sort of get a handle to yourself in Futures world. So when I poll this future, there's going to be some magic that makes sure that this value sort of points to myself, points to sort of this executor, if you will.
Oh my gosh.
It's not quite this executor. It's but you can think of it as this executor for now. When I call poll can call this method to get a handle to basically the current executor. So that's what this task is. Again, it's not really what a task is, but it's fine for now. That task item it gets, it can give away to whoever it wants, right? It can send it to a different thread, it can do whatever. It has to be the same process, of course, but generally it's going to like give it to some other thread. And then that other thread is responsible for, at some point, calling notify on that task. And what notify means is you previously couldn't make progress, but now you might be able to make progress. Right? Does that roughly make sense? So here,
I do.
we're not actually going to get into that because it's annoying. And so you can sort of think of this as we're going to poll all the futures, and then we're sort of going to go to sleep. So at the end here, it's sort of going to be a, let's call it a sleep. It's not actually a sleep, right? Let's call it. So here, the thread is going to go, I polled all the futures, all of them said they were not ready, so I'm just going to wait until one of them is able to make progress. And then on the side, there's going to be sort of meanwhile here, meanwhile, there's some other thread somewhere, like some other thread T notices that, say, a network packet arrived. And in particular, it noticed that a network packet arrived that this future that we polled, the returned not ready, was interested in. Right? So again, think of a future of something like a TCP connection, right? If this is a TCP stream, then if a packet receives for that TCP stream, then the thread somewhere that's like monitoring the TCP streams is going to notice, oh, a thing came in, and this thread, when it returned not ready, it took its task handle and gave it to that thread. So that thread knows that when something comes in on this TCP connection, I have to wake up that task. So it calls task.notify. and that task.notify is going to unblock this thread. Again, this is not actually thread park. There's some other mechanism that we have, sort of wait for task notify to be called, right? And now you can imagine this being even more sophisticated. So for example, instead of just having one task that we give to all the polls, we actually sort of keep one task per future. So let's write some sort of pseudocode here. So here, as the executor, I'm gonna this. Task.push, sort of task new, right? I'm not going to say what's in a task. There's some stuff in a task that lets you notify it, right? But let's imagine that I could sort of create new tasks on my own. Like you could easily imagine a task be something like a mutex.
Notify the executor when the result is ready isn't something similar to a callback strategy.
So the notify is not necessarily the future is or when the result is ready. Notify just means I think you can make progress now, right? So imagine you have a TCP stream, right? So a TCP stream is a future that doesn't return until the entire stream goes away, right? So in that case, if the TCP stream future gets notified, what that really means is just there's maybe something for you to do now because I received something or I sent something or something happened, right? And so you might want to check in on your stream again. So imagine that for every sort of top level future that we have, we create a task. And then here, what we're going to do is sort of task set current. Tasks I. And then down here, we're going to do something like, here, if I continue. Don't poll futures that can't make progress, right? So the idea here is that here F must have arranged for tasks I, its task, to be notified later, right? So this notion of a task both means that we know that there's no reason to poll a future that can't make progress, right? If we haven't heard a notification for it, then there's no reason for us to poll it. And then just before we poll it, we sort of set this magical thing that sort of sets what the current task is, and then we poll. So now if the poll tries to get a handle to itself, to its own task, it will get tasks I. And so if it gives away that to some other thread, this might be a clone or something, imagine that's a clone. Then if it gives away a handle to that task to some other thread, then that's really a handle to tasks I. And so if that other thread detects that there's something relevant for this future, it's going to notify. It's going to notify tasks I, which means that the next iteration we go through this loop, tasks I.notified is going to be true, so we are going to poll again, right? But notice what this means is that if a poll fails to get someone to notify it, it will never be called again. And so this is why part of the contract for poll, if you implement a future, is that you must have arranged for yourself to wake up again. If you don't, poll won't be called again. You won't get to make any more progress. And so down here, you can now imagine that we actually let this be a busy loop, right? The thread is just going to spin, and it's only going to poll on things that are ready to make progress. And then eventually, at some point, all of the futures are going to complete, and it can sort of go on its merry way. Of course, you could also imagine that this could be more efficient, right? Like down here, it does something useful. But we don't really know what that useful is yet. Like currently, let's just have it busy loop. It seems like the tricky part in all of this setup is to find some way to have these tasks be notified, right? Like, how do I get something
Alrighty. Yeah, sorry, I have to do some business calls today, which is actually unusual for me. So yeah. Let's see. Quickly, I have to look up some shit. Okay. All right. Let's go.
To be notified. Now, futures doesn't actually, the futures crate doesn't really talk about this, right? The futures crate is only about expressing things that are asynchronous and the mechanisms that you use for waking things up. It even has, down here, executor. So an executor is basically the thing that we wrote here, but executor here is really just the definition or the types that you need in order to write an executor. So notify handle is sort of, you can think of this sort of akin to task. Like notify handle is the thing that we're going to make, that we're going to set as the task that someone else is going to be able to call notify on. And internally, it's like, I mean, who knows what it is internally actually. Unsafe notify. Gee, that's helpful. Right, so the idea here is that if you are an executor, this is the with notify, right? So with notify, this is really going to be something like executor with notify, right? And this up here is not going to be task new, but it's going to be notify handle new. But all of this, and you notice that notify handle also just has a notify. The ID here is so that you can have here. So actually what this does is, instead of having a vector of these,
it's so deep, oh my
create
gosh.
your own notify handle. Well, let's ignore what this unsafe inside of it is. Yeah. And then down here, executor with notify. So with notify is what should you do? So notice it takes a notify, which is going to be, or I guess this should be a notifier. So notice this is all still really just the task stuff, but now we're actually fitting into what futures does. So it's a notifier, an ID, which is going to be an identifier for the current future, which in our case is just the index into the vector, and then an F, where F is oh, that's fine. The closure F will be executed. Right. So really what we want here is with notify says, just give me a notifier. I will set all the task stuff up for you and then call whatever you give me in this closure. In this case, what the closure is going to be is f.code. So we're going to match on this whole thing. And so notice how this is basically the same as what we wrote, just written without sort of the additional vector and all of this stuff. So the futures internally, the future stuff is written to have very low overhead. So you don't want it to do lots of vector allocations and whatnot. In this API, now we just have this single notify handle, and then we have these unique IDs that we use to figure out what's going on. And then notify handle. Notify? I think that's what I want. Specifically, what's the So the real way to do this is just so we actually now that we're decently close, we might as well do this anyway. Notifier is going to be arc new of something. We're going to give that to this. So you can create a notify handle by giving it basically a thing that implements notify. It just happens to require that there's an arc here so that it can easily make more of them, right? So imagine that you're creating lots of futures, then all of them need a handle to the same notifier for your executor. And so an arc seems like a reasonable thing for that to be. And then we need to implement the notify trait for what we give it. So in this case, this is going to be like an E notifier. And we're going to do this in the stupidest way. So my notifier. So my notifier is really just going to be, what is it even going to be? A mutex of a vec of a bool. And this is going to have an arc of a mutex of a vec of a bool. Again, this is a really stupid implementation that has all sorts of overheads, but my hope is to give you roughly an idea of what's going on. So here what we're going to do is we're gonna just use a mutex over a vec, and that vec is just gonna have sort of store this value that we use this notified, right? Whether it's notified or not. And we're gonna say that initially we should think of all the futures as being notified. We want to pull all of them sort of the first time, otherwise they never get a chance to sort of set their notifiers. Right? So this is just a my notifier, and we're going to give that in, and then we're going to implement notify for my notifier. And the notify trait does these things. Writes implementation for those. And the main thing it does is have this notify method. So this is, think of this as if something that's been given a task. So remember how in poll you can do task current, which gives you a task, right? And then on that task, you can call task notify. So T is a task, then you call T.notify. If you call T.notify within this poll, what that's going to end up doing is calling notify on this notifier with this identifier. And so that's what's happening here. And then let's just imagine that the way this actually works is this is going to lock the mutex, then it's going to set that index to be true. And down here, what we're going to do here is self.0.lock. So that is the same the same mutex. We're going to lock it. We're going to look at I, and if the ith element is true, sorry, if it's not true, then it hasn't been notified. I guess we could here do this. And then, of course, the moment we choose to pull it, we now want to say that it is not ready anymore. Otherwise, we're just going to keep calling it. Does that roughly make sense? Right? So the idea here is, I guess this should be was notified. If the ith future was notified in the past, sorry, if it was not notified, then we don't need to pull it. And now we said it was notified to false because we're about to pull it, right? Okay, so now we have all the infrastructure that's necessary for notification, which is sort of causing a thing to wake up later. And that's all that's really
should I put another TNT thingy on here because all the withers are on this side, or can I move them somehow? Because sometimes they all track one target and then they seem to be moving really fast and in bulk, but I don't know how to manually cause that. It would be nice to get them all under my... Where's my... Did someone destroy... Well, I guess taste is personal regarding his chat message. But did someone destroy my thing again? Sure. How inconvenient. Or was it a wither? I don't know. Anyways, so building these TNT machines to kill the withers doesn't seem to be efficient. If they would stay and it would increase the damage over time and it would be like an investment that stays, then they could make sense. But since they break all the time up there, it might be faster to kill the withers by hand, but that takes forever. Maybe, can I get all these withers like attracted, what the heck? Like just far away. So that I don't care that they are there. They don't really follow me. I don't know when they move that fast and all together. What causes this action? I feel like animals or something like that they track can cause this, but I don't know. Anyways, so yeah, whatever.
Find an executor. So the way we got into this was, the question is, how do we get notified to be called, right? All of this infrastructure we've set up, all that really does is, it's a bunch of infrastructure so that when you call poll, you have a thing that you get a handle and you can call notify on that handle. The question is, who calls notify on the handle? How do you know when you can make progress? If you return not ready, who's going to wake you up? Who are you going to give this task to? And that is what brings us from Futureland to Tokyo. So Futures defines, as we talked about, sort of the general principles for, or the general interface for how to deal with asynchronous computation, the interface for things like tasks and notifiers and wake-ups and executors. But it doesn't really define any implementation details. Right? It doesn't give you an executor. It doesn't give you some other thread that's going to wake you up. It only defines the interfaces. Tokyo, on the other hand, is an implementation of both an executor and sort of the other infrastructure that you need in order to make things wake up. That is basically what Tokyo provides. And in fact, as you can see from the documentation, Tokyo is an event-driven, non-blocking I/O platform to write asynchronous applications for the Rust programming language. And so in some sense, what Tokyo is this business, but this business was not too hard to write. Of course, it's a lot harder to write an efficient implementation, but it's basically this. Where Tokyo shines is it also gives you this thing that's going to wake you up. And in Tokyo, that thing is called a reactor. Let's go to reactor. Or there are many things that can wake you up. The most common thing that can wake you up is that there's some kind of I/O that you were waiting for, whether it's a disk read or write that finished, a network read or write that finished, like some socket is ready. So like that kind of I/O is the most frequent thing to wake you up. There can be others, and we'll get into those later, like timers, for example. So actually, maybe we should do timers first. No, let's do I/O first. Right. So again, think of the case where F is a TCP stream. I guess while we're here, we might as well make this proper. So this is going to be F. It's going to be F item. It's going to be F error. Where F implements feature. Right. Remember, this requires all of your features to be the same type. This is not true in sort of the real implementations. But you sort of get the idea. Of course, normally you also wouldn't return like a vector with the index is one of the values that's also really weird. But such is life. Okay, so the question is, how can we do, like, what is a reactor? Well, a reactor is basically a thing that you can give a tuple of a task, so a thing to wake you up, and sort of a handle to something the operating system is going to tell you is ready. So in order to understand this, we first need to talk a little bit about how asynchronous I/O works in the first place. How much of it changes future 0.3? So we'll get into that a little bit later, in part because future 0.3 isn't fully stabilized yet. That's why this RFC is open down here. It is basically the same in terms of execution model, but there are some changes to the interface that we'll get into later. The reason I want to do it later is because Tokyo uses future 0.1, and so I want to talk about it in the context of Tokyo first, and then we can talk about how this is changing going forward. Okay, so to talk a little bit about how asynchronous I/O works, in sort of, it works differently in different operating systems. The basic idea is the same. So if you have some kind of I/O handle, I can draw. Yeah, let's draw. Time for some drawing. Who needs code? So, I'm a terrible drawer. You're going to regret this. I'm going to regret this, I guess. So, you, in most applications, you sort of have, I guess I need color white. Down here, we have the kernel. Wow. Writing on this is hard. So down here we have the kernel, and then up here somewhere is your application. Woohoo! This is your application. It's a great application. You're super happy about it. Now, let's erase that. No, it's fine. What did I do? So you have your application, you have your kernel, and your application has a bunch of outside connections, right? And the kernel, really, those connections aren't to your application, right? This is not really true. In reality, there are a bunch of connections that your kernel knows about, and it sort of has a connection, or sort of ties each of those connections back to your application. And the way it does that is that it internally has some identifier for each of these in Linux and Unix and Mac OS, not in Windows, quite sort of. So the idea is that each of these have sort of an identifier. Let's just imagine that they're numbers. On Linux, they are in fact numbers. And your application, when you call, for example, TCP stream connect, what you really get back is just a number. So the kernel tells you, I connected and I gave it ID 1. And so when you do connect here, in this case, imagine that you have 4 things already. You connect to some server. The kernel is eventually going to tell you, OK, that's now 5. And it ties that also to your application. Identifier, yeah, so this identifier is the file descriptor in Linux. In other operating systems, they're called different things. But this is basically a number that identifies this particular I/O resource in the kernel, or this resource in the kernel. So connect is going to give you 5, and then when you later, so let's say in your application you said something like x is connect, then what x really is storing is just the number 5, nothing else. When you call, say, x.write, and you give it, say, foo, like you give it some string foo, what this turns into is really just you do a write system call. So a system call is you tell the kernel to do something. So that's the primary interface between these two is called syscalls. Really what you're doing, and this is usually a C API of some kind, so that's really just calling the syscall write with the number 5 and foo. Right? So anytime you do an operation on X, you're really just doing an operation on a number. But the kernel knows about the mapping between these numbers and the actual underlying resources. Do all of that roughly make sense? So where this now gets tricky is imagine that I want to do, let's clear this. So, and then we draw just the basic things that we need. So we still have the kernel down here. It has a bunch of resources, it has numbered them, and your application is up here. Draw it a little bit bigger this time. And it knows, you think of it as like, it knows all of these numbers, but that's all it really knows. You can ask the kernel more things, like if you wonder what IP address did I connect to, there's like a system call you can do that says, hey, tell me more about number 3. So in our future space world, right, we have these numbers 1, 2, 3, 4, which we've mapped to say X, Y, Z, and a Norwegian letter. Why not? I also chose the middle of the 3 Norwegian letters because it seems like more fun. All right, so we have these 4 variables that are all TCP streams, and internally they're really just storing like 1, 2, 3, 4, but our application doesn't really know that, right? It just knows the names. And now we have some future that's computed over all of them. So imagine that we're going to do like x.read. We're going to do the same for y, we're going to do the same for z, and we're going to do the same for right? So all of these 4 we're going to do a read on. But of course, in our asynchronous model, we don't really want to first do x's read, then do y's read, then z's, then us. Instead, what we want to do is sort of do all of the reads at once and just wait for whichever comes back. This turns out to be a little bit tricky to do, right? Because the system calls we have are a read, right? It's a read of some number here, right? That's going to give you back some data. This isn't actually what the system call interface looks like. There has to be a buffer and whatnot, but generally, like, you can think of it as you do a read, you give it the number, the resource you're operating on, and it gives you back the data. So given that interface, how do we map that to doing these in parallel? Imagine we only have one thread. We want to execute these 4 in parallel on one thread. When you do a read, like, that's going to block you. And so this is where the idea of non-blocking I/O comes in. The kernel has this additional parameter in here that's called usually flags. It's different on different operating systems, but let's just talk about Linux in general. It generalizes to Windows somewhat. The interface is a little bit different, but the idea is mapped pretty well. So you can pass in flags, and one of the flags that you have is one that's called, I think it's O non-block. Now, this flag is not actually set on read, but rather it's something that you set on the socket. So you say that from this point forward, whenever I do an operation on, say, socket 4, I want that operation, if it were to block, so if there's no data to read, I want you to return saying there was no data to read, instead of just like blocking. So normally, ignore this then. Normally when you do a read, if there's no data available, the kernel is just going to stop that current thread and just not return until there's data. If the socket that we're reading, like here, let's imagine we set this non-block flag on 4, then if this is 4 and there is no data, like there's no data at all, what the kernel is going to do, so imagine here I do a read of 4, and 4 has no data. What I'm going to get back is basically an error from the kernel, and that error is going to be of the type would block. This is, again, different on different operating systems, but in general, there's some error message that said, you told me to read, there was nothing to read, and you have told me not to block on 4, therefore I'm just going to tell you this is an error I would have blocked. And similarly, of course, we could set this non-block flag on all of these resources. So we try to read it from any of them, and it doesn't succeed, we're just going to get would block. Okay, that's all well and good. So what this interface would give us is we could just sort of try to read X, and then if it returns data, that's great, then we can continue. If it doesn't return data, we then immediately go to Y, and we try to read from Y. And so now we're just sort of polling them, right? So this is very similar to the API we had in Futures. We're just going to sort of try each one, and then if none of them had anything, we go back to the beginning. We try each one, we keep doing this. But that is really inefficient, right? So imagine that this is sufficient though. Imagine that we have our executor down here, right? And we have these futures, and each future is trying to block on a different stream. And so remember how the core issue is who's going to wake you up? So imagine that this future spins up another, or doesn't even spin up another thread. No, sure, let's imagine it spins up another. So there's a second thread in our program. And what that thread is going to do is it has sort of a channel into it from here that tells it a task and a one of these identifiers. So an ident. This would be a file descriptor, right? So every future, if you have a future you call poll and it decides that it needs to do some reads from the network and the network isn't ready yet, it sort of sends its own task and the file descriptor wants to wait on to this thread. And this thread is really just looping, and in every iteration of the loop, it's doing like for task and FD for each one, then like do a read on FD, and if this returns anything that is like not would block, then notify. I guess notify that task.
Shit.
Right? And of course, you would have to adapt this to also do things like deal with other things than reads. You would also have to make sure that this read doesn't actually read anything, right? Because if this read actually reads, say, 100 bytes from this file descriptor, then when we then go back to pull the future and it tries to read, those 100 bytes would just be gone. And that's not okay. So writing with this interface is actually not straightforward, but you could imagine you could implement this way. But this is, of course, really inefficient, because it means that, first of all, you also need this other thread, and this other thread is going to spin doing system calls. And imagine you're waiting on, say, 1,000 sockets, then this loop is just going to be trying to read from every single socket over and over and over again. So it's the time it takes. So imagine that you're doing the spinning through, right? You're just reading from all of them until one of them returns not anything but would block. And then say the like 500th socket is now ready. But you just checked the 500th socket right before it came ready, and you're on like socket 501, then this future wouldn't be woken up until you've walked through all the other file descriptors and then gotten back to it. That seems really inefficient. And so this is not really the API we want. This is the API we'll want to use inside the future, right? If I am a future and I'm a TCP stream and I'm trying to read some data, I would do read, right? Because I need to read. And if I get would block, what that translates to is really, I want to sort of register my handle with this thread, and then I return not ready, right? So that part is all fine for using read inside of that, but for implementing this thing that wakes people up, we don't really want to use this sort of non-blocking interface, because it's really inefficient and also not entirely clear how to even do correctly, right? For example, imagine that you had to do this for, you would have to do this for writes as well. What would you write here to test whether it was ready to write? You write like no bytes? Is that even legal? I don't know. I think then it would never block, because it says, you asked me to write 0 bytes, I did it. So you wouldn't even know whether it would block. Okay, so this is all clearly kind of stupid. So this interface is not really what we want. But there is a better interface. Ooh, that's a good question. Can I erase just something? This is a new drawing program. Oh, that's awful. Can I somehow change the brush? Get a big one. Yeah, great. That's maybe larger than I wanted. This goes away. All right.
How stupid I am, bro.
No. D, great. So, this comes back. All right. So we want a better, basically we want a better interface that lets us do this wake up business. And it turns out there is. There are different interfaces to use for this for different operating systems, but we're going to talk about one called epoll. epoll is what you end up using on Linux, and all of the other operating systems have mechanisms that are not quite the same, but have a similar end result. So epoll is this interesting system call that you can sort of think of as you give it a bunch of file descriptors, and then you give it a bunch of sort of operations, but not the actual read or write operations, just sort of says, can I read, or can I write, or let's imagine just those two, right? In fact, because we're allowed to cheat, we could make this a lot nicer. So we're gonna have something like, it's gonna be given a tuple of fd and op, where op is either a sort of can read or write. And then it's given multiple of these. And then it returns a list of FDs. So let's go through this in a little bit more detail. So the idea here is that if I'm a thread, I can call epoll and then say, hey kernel, I want you to block me, and then I want you to tell me if any of, for each of these pairs, if any of them, that operation is, this operation is ready for this FD. So, so this operation is ready for this file descriptor, right? And what kernel is going to do is it's sort of going to internally
Oh boy.
to sort of say, hey, so imagine that we call this with like for and read and one and write. It's going to add a marker to one saying, hey, if you detect that I can now do a write, that a write would no longer block if I tried to do it. So basically the space in the outgoing connection. Or into for, hey, if you notice that there's data available to read, then the kernel is going to keep sort of a little thing over here, sort of like a notifier. This is very similar to what we did for futures, just internally in the kernel. So it's going to, I guess it's not going to mark on these. It's going to mark on 1 and 4, and then say, if you see a write, then come poke me. If you see a read, come poke me. And then this epoll is going to block until this thing gets poked. When it gets poked, it will return the epoll. And it's a little bit smarter than this, in fact. Epoll is a system call, yes. So it's similar to read and write, except that this is the interface instead. And in fact, it's a little bit smarter. It initially, when you first call it, it's first going to check all of them. And if any of them are ready, it's just going to return straight away, right? So it might tell you immediately that, yeah, 4 is ready for reading and 1 is ready for writing. Go ahead. That might just be what it returns. But if it detects that none of them are ready yet, then it adds these watchers. And what it returns is these are the file descriptors that are ready. I think it even maybe gives you the ops as well. So what this returns is like 4 is now ready for reading. Maybe 1 wasn't ready for writing yet, but 4 is now ready for reading. And now you might see how this fits into our whole executor ID here. So because all we really have to do is have this other thread. It's still going to be given task and ident, and maybe now it's also going to be given an op, right? And then inside of this, inside of this other thread that's going to wake things up, we're going to do something like this. Actually, here we might switch to code again. All right, so we're now looking at what's inside of that other thread. Just do it at the bottom. So this other thread, like this is going to be the reactor thread. And the reactor thread, when you start it, you're going to give it, what are you going to give it? You're going to give it like a channel. Not like really going to be a channel. Let's imagine that it's a channel of task and a file descriptor. FD equals file descriptor. And an operation, where operation is read or write, or I guess read or write. You can think of this as can read and can write, but read or write. And internally, what the reactor thread is going to do, no loop, it's going to operate forever. It's going to keep sort of waiting for, which is going to be, let's imagine that it's a hash map. No. No, sure. Let's imagine the hash map. From FD and operation to task. On every iteration of the loop, it's going to make like a select set. So this is, select here is the sort of set that we're going to give to epoll. And that's going to be waiting for .keys.collect. And then it's just going to call epoll. Remember, epoll epoll returns a set of file descriptor and operators, right? So this is going to return something like fd and op in epoll select. So we're going to do an epoll over all the things that we're currently waiting for. And then for everything we get back, we're going to do task is waiting for .remove the op. And I guess it's going to be the way. .notify. And we might even do something while let some off is equal to notify me. So we're also going to sort of accept more of these if there are any. Then we're going to do this, insert the op. So this is our reactor thread. Right? It doesn't really do all that much. It just accepts new things to watch for, and then it just watches for all of them. And anything that's ready, it will notify. In fact, when you look at this, why does it even need to be a thread? Why does this have to be a separate thread? It doesn't, right? Here, remember how when we were writing our executor, remember how when we were writing our executor, there's like some piece of time during our executor where we might not have anything to do. We've pulled all the futures, all of them have said that they're not ready, so how about we just do some useful work, like run the reactor? So instead of having this separate reactor thread and have this channel, how about we just sort of do this? Keep waiting for up here. And then down here, we're just sort of gonna, whenever we know that there's nothing more to do, I guess technically, you have to be a little bit careful here. Sorry, you could also imagine, well, okay, I'll ignore that for now. So what we're going to do is whenever we know all the futures can't make any progress, then clearly we need to wait for something, right? We need to wait for something to happen so that they'll be ready again. And why don't we do the stuff that's necessary to make them ready again? In fact, it's totally fine for us to block until they're ready again, which is what we're doing here, right? EPOL is going to block on all of these select things, on everything that everyone is waiting for. And then whenever EPOL returns, that means something is now ready. And so we're just going to notify those. And then we're going to go back to the top. And then we're going to go through all the futures again. So now this is all still single-threaded. There's none of this extra sort of indirection through a channel. All of that is unnecessary. In fact, because all of this is now single-threaded, we don't really need this arc in mutex. But we're going to leave it in because getting around it is a little bit annoying, but just believe me that it's possible to get rid of that these extra indirections. We do have one issue though, which is now because we got rid of that channel, and even if we did have the channel, how does the futures poll send some, like, if we still haven't said how it adds something to waiting for, right? How do I, as a future, I'm given no arguments to poll. How do I sort of say to the wider world that, hey, I want to wait on this file descriptor? I have no way of communicating that. And so in Tokyo, with reactors, this I might need process Tokyo reactor. So Tokyo is split up into many subcrates that deal with specialized things, and then Tokyo is sort of putting all of it together. Why are we dropping was notified? Oh, sorry. The reason we dropped was notified is holding the lock, and poll might try to notify itself immediately, and then if we're still holding the lock, that notify would block, and would never be released because we're still holding the lock. So it's just releasing the lock. We could easily do this as well with just this. Just to prevent a deadlock. Oh. Right. So let me save this.
What did I just do?
Yeah, sorry. So Tokyo is broken into lots of small subcrates. Basically, there's one for the Tokyo executor, there's one for the Tokyo reactor, there's one for the Tokyo timers, and the Tokyo crate itself just sort of brings in all of these things and is intended for anyone who uses futures. If you are implementing futures yourself, you should depend on the individual crates, like Tokyo reactor. And that's because that has all the stuff that you need to be able to notify. And so here, we'll see that in reactor, sorry, yeah. So remember how we have this executor with notify, right? Which sets sets basically the task that's going to be returned by task current. Well, Tokyo defines this reactor with default. So it has handle, which is a handle to a reactor, and handle has a handle current. So this is very similar to task current. So inside of a future, there's also going to be the ability to do handle, Tokyo reactor handle current, and that's going to give you back a handle. And a handle is basically. So if we look at handle, we look at reactor. No, sorry. Where's the? Yeah, so you can create a registration. And a registration is basically like this this tuple that we have of task and file descriptor and operation. And you say register with, and you give it a handle. And the handle is going to be the reactor. And so this is saying, sort of giving to the handles, telling the handle, hey, this is one of the things I now want you to notify on. And so given that we're implementing our own handle, Tokyo isn't, because Tokyo just provides us with a reactor, this isn't an interface that we can write ourselves, because Tokyo just provides you an implementation, right? But if we were to, the idea would be that we create a handle, and handle has a method. If we could look at it internally, I guess. Might not be helpful, actually. It's a lot of very optimized implementation. But the idea is that inside of the future, you can call handle current to get a handle to the reactor. In our case, the reactor would really just be waiting for, right? So this, I guess, would also be an arg mutex probably. And then given that handle, of course, now you can add something to waiting for. And if we go back to here, you notice that this with default. So in addition to doing this, we would also do Tokyo reactor. Or if this was sort of generic, it would just be reactor, right? And we would say this with default. We would sort of do like my handle, like we'd make our own handle. Ignore enter for now. And the closure that's going to be called is this. Right? And so this sets what handle, I guess this is going to be, yeah. This sets what handle current is going to return, and then my handle here would really sort of be waiting for it. Right? Does this sort of make sense? So inside of poll, we now have access to the current task for wake-ups through task current. We also have access to the current reactor through reactor handle current. And so this we can use to notify. This we can use to put something in waiting for, which will also be the cause us to be woken up later. We'll get to future 0.3 later. Okay, so that is basically all the infrastructure that we need in order for poll, for futures, to be able to have themselves be woken up later when I/O happens, right? So inside of a future, where can I, down here, I guess. So let's say we have some struct foo, which internally contains like an FD, a file descriptor of some kind. And then we're going to implement future for foo. Its item is going to be nothing, its error is going to be nothing, because whatever. It's not important for this particular discussion. This returns, we're going to make it explicit just so we don't miss anything. Right, so we're doing this. Actually, let's imagine that this is standard TCP stream, with the exception that, but with non-blocking set, right? So this means that if you tried to read from it and it failed, it would give you, it would just say would block. So what this poll is going to do, let's imagine that what we really want to do with this is just print every time there's stuff coming back from it. So poll is going to do like self.fd.read, right? Now let's match on that. That could be okay, which is it read some number of bytes, right? And if that's the case, it's just going to print line that like got this many bytes. Again, this is with imaginary types. If it got error and the error was like an IO error would block. So if it got a would block, then it's going to return async not ready, like this. And if it got any other error, then it's going to return that error, right? If any, I guess what we could do is like IO error closed. Again, this is not actually how streams work, but it's not important. If we got closed, then now we know that we're not going to get anything more. So now we're going to say that this future is ready, it's finished. There's nothing more to do for it, right? It's not going to do anything more that's useful for it. So this might be the sort of naive way to implement poll, but of course now we have no way of waking ourselves up. So here we've returned not ready, but we haven't arranged for ourselves to be woken up, so this implementation is clearly broken. And so here we're going to have to do something to make sure we are woken up. And in fact, it turns out that making ourselves be woken up is not that hard anymore now, right? We're going to basically do handle current. So this gives us back the reactor, right? And then let's just ignore Tokyo for a little bit right now. So reactor dot sort of register self dot fd. Wow. Fd. Imagine that we could do this, right? Sorry, that's still not sufficient. Yes. And we're going to have to give it task current because it needs to know who to wake up. And now if you imagine, if you sort of squint at it, reactor could totally be waiting from up here. So that when we call reactor.register, it really just sticks the file descriptor and operation into there and the task current as the value of that map. And now we know that if it's ever possible for us to read again.
FK for a second. I had to cry in the kitchen, I'm sorry.
We'll be woken up appropriately. Even this code is a little bit broken though, because imagine that we do a read and then we get some data. Then of course, well, this wouldn't type check in the first place, but I guess here, what do we return in the OK case?
Where the fuck am I?
Like the read succeeded, and so we got some data. Now what do we do? Well, we could return OK not ready to indicate that there's going to be more data, right? It hasn't been closed, so we might get more data. But then, of course, then we have to do this in order to maintain the contract. And that might be fine. Like, this would still work just fine. But imagine that there's a bunch of data available. We read a little bit of it. We don't really want to have to go through the entire song and dance and sort of go to sleep, put this on the reactor does epoll, we get woken up, and then we do a read again, if we could just immediately read again. So actually what we're going to do, and this is usually what you end up with in poll implementations, is we're going to loop.
How did I?
So as long as it's possible for us to read more data, we're going to do it, right? So remember that read will never block now. Read will always return immediately. If it would have blocked, it returns would block. So the read is going to come back, we're going to read some bytes, and then we're going to immediately try again. And it's only when the read tells us there is no more data now that we register on the reactor and then return not ready. Right? So I guess this is going to be something like print bytes ready, because that's what it does. And this is actually the implementation of a future that you would have. Now, that's only somewhat true, because the interface for reactor is not actually this. If we look at reactors, when you get a handle, the only method on handle is current. It implements some other things, but that's basically unhelpful. Instead, what you do is you create something called registration. Registration is an IR resource, right? So this would be a file descriptor and an operation, for example. I guess actually there might be a higher level background maybe? No. Hold on, dude. Yeah, this one. Yeah. So you would instead do this. So you would do something like pull evented new with handle, and then you would give it the FD, and then you would give it the reactor. And then what does that give you? Dot pull read ready. Like so. So that's how you would actually write that code. And if, right, so if you look at what this does, it creates so poll evented is basically a struct that contains things like the file descriptor.
Spider.
So it's basically the same, it's just wrapped in types. And new with handle is saying, I want to listen for this file descriptor on this reactor, and then I want to check, I want to wait for ready. Now this actually returns, if we look at it, poll read ready, returns a poll of, I don't know what ready is here. Oh yeah. So this returns some stuff that returns either async ready with a thing that we're going to ignore for now, or it returns OK async not ready, or it returns error. And if we look at where is it here? If the resource is not ready for a read, then not ready is returned, and the current task is notified once a new event is received. And this last part is the crucial bit that we needed, right? Remember, the contract for not ready is that you have made sure that you will be woken up again. If we call poll read ready and it returns not ready, then we know we're fine. So here, if we get not ready, then we know that we can just return OK async not ready, and we know that the contract is maintained. If we get error, then we just return that error onwards.
Oh my gosh!
If
What?
we get ready here.
What happened to the wall?
So
Is it
first
never?
of all, keep in mind you will never have to write this code yourself because there is.
Where am I?
Tokyo,
I'm here. I think it was never finished.
Does all of this for you. You will generally never have to write at as low as of a level as interacting with reactors. I don't think I've written any code where I had to interact with a reactor directly because you just go through things like TCP streams. But this is more, the goal here is that you understand what's going on behind the scenes. Okay, so async ready basically tells you that if you were to try to read now, you would actually get something. So this is really just saying try again. So this is like the file, so this is really, it's often referred to as a socket. The file descriptor for a network thing is called a socket. So this, in this case, what this is saying is that the FD socket became ready between when we read and called read ready. Now, of course, the actual implementation is smarter than this. It doesn't call read and do this read and sort of do an extra system call. It doesn't have to do that. It's smarter than that. But in our implementation, this is fine. And so notice that this poll now follows our contract, and it does all this registration with the reactor, and all of it just does the right thing. And then down up here, we're just going to, if you imagine that this handle is really a handle to our waiting for, then this all does the right thing. And in fact, now we're getting pretty close to what Tokyo does. So Tokyo has this idea of a runtime. So a Tokyo runtime is basically a thing that provides you with a reactor an executor, and then also a timer. So all of the things we've talked about for reactors so far also applies to timers, right? I imagine that I have a future, and I want it to resolve 10 minutes from now. Then who's going to wake me up in 10 minutes? Right? You could spin up another thread and have it just check the time all the time. But in reality, that's not really what you want to do. And so instead, what you do is at the bottom of each loop like this, you sort of check whether any of your timers have expired. And if they have, then you notify the appropriate tasks. If they have not, then you go down to epoll. And then instead of just using epoll, you use epoll timeout. And then you give like the min remaining timeout here. So what epoll timeout does is it will block in the kernel, but it will block for at most this long. And so the reason you want to do this is to ensure that if there are timers you're waiting for, you'll sort of get back to them in a timely manner. Imagine that the things you're epolling over, all of them just block for hours and hours. If you just blocked in here, you wouldn't check the timers again for hours and hours, which means that the timer that's supposed to go off in 10 minutes wouldn't go off in 10 minutes. And so instead, you will do epoll timeout, and here, the epoll would then return in 10 minutes, and then you would go through the loop, see that some of the timers have expired, notify them, etc. And timer is very similar to reactor in basically all the ways. Timer. If you look at it, there's a with default, and there's a timer handle current, right? So the setup is exactly the same as for I/O, like the interface for interacting with it. And then of course you end up with here Tokyo timer with default whatever, and then this closure. Right? So you can see that this starts adding up a lot because you have to give it handles to all the different ways in which it can wake up. And so this is why we have this notion of a runtime now. And a runtime is really just, it gives you all these three things. Is it possible you rarely reach that bottom part because there are many futures in the queue? Yeah, so imagine you have tons of futures and they're always all ready. You basically need to find the right way to switch between dealing with the futures and driving the reactor or driving the timer. We'll get back a little bit to that question then about what do you do if there are lots of futures. But the basic idea, or the thing to keep in mind is the executor does have to deal with this, right? It needs to know that sometimes it needs to like not execute futures because it has been a while since it's checked its other stuff. This is basically the idea of fairness, right? You want your executor to always make progress, and if it has lots of futures that it's calling poll on, then it is making progress. So in some sense, it's doing the right thing. But what you're asking about is, but that means that there are some things that are not going to be notified, right? So you're not providing fairness. You're not allowing all the futures to make progress. Instead, you're taking just a small set of the futures, the ones that are currently ready, and just executing those. And so, again, you have to think of this as if you only have one thread, then if it's doing work, then it's being productive. So is it then better to check the timers and work on some other futures? It's unclear, right? You're already using all your cycles, and so why is it better to check that other future that depends on timer? Maybe it's not. But it is true that means the timers might take a while to fire. They might not fire straight away. And so usually the executor has some kind of almost like time granularity of, in fact, if we look at Tokyo timer, I think it says, where is it? Delay maybe? Delay has a resolution of 1 millisecond. So if you want
that
to
didn't work
timer
out
that's
too well,
greater than
did
that,
it?
it's not going to give it to you. I don't remember exactly the details around this. I think it's also related to the fidelity of the granularity of the timestamps you can give to like epoll timeout. But in reality, the executor also has to make sure that it checks the timer that often. Okay, so the notion of a runtime is really just all the stuff that we've written so far, sort of all this with default, with notify business, and also all of the, so here, just like we had just like we had timers and reactors, we also have Tokyo Executor. And Tokyo Executor is basically the thing that we wrote. And no, that's not what I want. Right, so executor with default basically just calls into the future executor with notify. And there's a...
Fuck.
Where's right, so this is just all the traits that you need around an executor. And then the runtime provides an implementation of a reactor, an implementation of an executor, and an implementation of a timer. There are, right, so if you see what a runtime does, it spins up a, that's not true anymore. This documentation should change. Documentation is wrong. If we look towards the bottom of runtime, you see that there's a runtime here, and then there's a module called current thread. We're going to look at current thread first, because that's more similar to what we built, and then we're going to look at the default Tokyo runtime afterwards. So the current thread runtime is a runtime implementation that runs everything on the current thread, which is the thing that we've been writing so far. And at the heart of it is a runtime. And all that runtime does is basically the stuff that we wrote here, but in a much more efficient way. And so when you create a runtime, you just create it, you get back a runtime, and on that runtime, you can get a handle to it if you want. So this is a runtime handle, and a runtime handle lets you spawn futures. So remember how really early on we talked about how you can sort of do something like a.spawn future x. Spawn does not let you learn the result of a computation. Yeah, exactly. So if you spawn something, it basically means I don't care about the result of this computation, just make sure it gets run in the background. So this is usually what you would do with managing connections, for example. So imagine that you have a server, which is going to be a TCP listener new dot incoming. I'm going to listen on 4. Incoming gives you a stream, which we may or may not talk about streams. It's relatively unimportant. But think of this as like, this gives you a for each thing. So this gives you think of it, basically it gives you an iterator, but it's sort of an asynchronous iterator. So this returns a future, not an iterator. And then for each is going to be called for each new stream that we get. And basically what we're going to do is going to do Tokyo spawn. So Tokyo spawn is really just syntax for Tokyo, how do I want to write this? Sort of, for Tokyo executor handle current dot spawn future. So if I write this, it is really just that. Keyboards are hard. These are basically the same, except actually it's not executor, it's runtime. But you get the idea. And so in here, usually what I'll do is something like I'll spawn S. So S here is a TCP stream, right? And so usually I'll do something like my application handler over S, and I'll spawn that. So this is, instead of spawning a new thread, I create a new thing that has all the state for a connection. So this might be like client connection, whatever you want to call it. And so I create a new client connection over that stream, and then I spawn that client connection. So client connection itself is a future, right, that will resolve whenever the client disconnects. And that client connection we give to Tokyo spawn, and now Tokyo spawn is going to, or the executor that Tokyo has, is basically going to add it to the set of futures that we're operating on. So keep in mind, here we have run all, right? So what you could do is here, instead of having run all, you have a vector of f future. And this, instead of being run all, is just going to be a run. This is going to make us sad, so let's not do it. Sort of. Sure. Why not? So spawn takes an f, does not return anything, and just a self dot one dot push. That's all spawn BG does. Now, of course, this is not how it actually works, but you can sort of think of it this way. Right? So if you spawn an executor, you're really just saying, hey, by the way, also execute this thing, and I don't care about its result. Right, so here we're spawning that client connection and having it be run in the background, and Tokyo will just automatically deal with that. Where were we? I don't need these anymore, so I think those go away. So if you have a current thread runtime, so that includes a timer, a reactor, and an executor, all running on a single thread, then you now have a spawn method, which lets you spawn any future. And notice that it spawns only futures that do not have an error or item type, because you have no way of getting at its return type, right? If you spawn something, you sort of lose the handle to the future, so you don't know anything about it. It also has block on, which is give it a future, and it will give you back the result of that future. So think of this more akin to running that future directly, and then still running the other things. So the executor is still running, but whenever this particular future finishes, you're going to return it. Now, of course, because this is a current thread runtime, the thread can't do anything else while this is running. So if I call block on, it really is blocking the current thread until that future finishes. And then it gives me the result. And of course, because once this returns, this thread is no longer running that runtime, and so all of the futures that spawned on that runtime will also not make progress. The reactor is not going to make progress, the timer is not going to make progress, because we have nothing to run it. The current thread has returned and is doing something else. And that's also why this is run method. So run is sort of similar to our run all down here, right? Except that it doesn't return anything. Run is just going to operate over all the futures that we have stored, and it just assumes that they're spawned, so it's not going to return their value at all. So in fact, we could now write this sort of like, I'm not even sorry, it's not important. Run is really our run all. Why don't I see
the name leader in my health bars? I don't get it.
And block
Shouldn't it show the closest one?
Sort of like run all, except that it returns the result for a particular future.
I don't get it.
Namely the one you gave it. Okay, so that's all current thread runtime. And it's basically what we've written so far. But then, of course, the observation that came from the chat here as well was, what if I have many futures? Like I have lots of futures, all of them are doing stuff. Then it sounds like I need more than one thread. How do I do that, right? And that's when we get back to the Tokyo runtime itself. So remember how we looked at current thread runtime. There's also the general runtime. This is also what's used if you call Tokyo run and give it a future. Tokyo run is going to use the default runtime. The way in which the default runtime is special is that, again, this is not true, it uses a thread pool. Whoa, okay. Executor? No, I think this is Tokyo pool. No. Executor? What's it called? Thread pool. That's the one. So instead of using the current thread executor that we talked about this far, it uses the Tokyo thread pool executor. And the documentation here is pretty helpful. It says that this is a work stealing based thread pool for executing futures. It supports scheduling futures and processing them on multiple CPU cores. Users will not normally create one themselves, but instead will use it via runtime, which we've talked about so far. We're not going to talk about blocking threads for now. And so here is sort of the basic description. Each worker has two queues, a DQ and an MPSC channel. The DQ is the primary queue for tasks that are scheduled to run. task can be pushed onto the DQ by the workers, but workers may steal from the DQ. The channel is used to submit futures while external to the pool. Okay, so here we're going to need to do some drawing again. Switch back to white. So in this setting, you're going to have all of this is inside your application, and we're going to have your code here. So, as you can tell, this is clearly code. You can tell because there's a curly bracket. That's how you know it's code. And then what Tokyo thread pool does is it's going to make down here. It's going to start up multiple threads. Let's say that you have 4 cores in your machine. So this is a pool of 4 threads. Each of these things is a thread, as you can tell because there's a little thread on them. And each thread is going to have a queue. So, and your code, which has a somewhere in here, there's like a let RT of type runtime, right? And with this runtime, you have the ability to call .spawn and give it a future. And what this runtime really is, at least kind of, sort of, is a sender. So this is an MPSC sender. And so if you spawn the future, that future goes through the sender, and the sender just sort of points to the pool. Again, kind of, sort of. And actually, I don't think this is. Double check this. Right. And what's going to happen is every worker thread, this queue that they have, is a queue of futures. So all of these are futures. So each thread has a bunch of futures that it's executing. So this is similar to the sort of vector of futures that we were storing in our own sort of single-threaded implementation. So each of these futures, each of these threads has a reactor, has a timer. Unclear. May or may not have a timer. It might be that it spins up a separate thread for timers. I don't remember. But let's imagine that it has a timer. So each thread has a reactor and a timer down here, which is, remember, just a part of the thread. This is not a separate thread. Just like in our executor, the reactor and the timer are driven by the thread itself, just so with these worker pools. And so each of these workers is going to have the same kind of loop as we wrote in, so here, each of these is really, you can almost think of each of these as just a current thread executor, right? So each of these is basically one of the things that we wrote ourselves. They're basically indistinguishable. Their main loop is just take the next future from my queue, poll it, and then try to make some progress on these if necessary, or I think it polls everything that's in the queue. Like it walks its queue, polls all of them, and then puts them back on its own queue. And then after it's polled all of them, then it goes, color, like this one. So the steps for one of these is, here, one, poll every future in my queue. Right? So that's the first thing it's going to do. And then there's like 1.1. If ready, then remove. right? So if poll returns ready, there's nothing more to do for that future, so we just get rid of it. If on my queue, I don't know why I'm writing these. I don't know if the writing helps, but it's sort of, that's the protocol. Like for every future in my queue, I'm gonna poll it once, and then if it's ready, I get rid of it. If it errored, I get rid of it. Otherwise, I put it back on my own queue. After I've walked my own queue, then I'm going to check the reactor, right? So this is just like trying to make progress on the reactor. And then 3 is basically go to 1. Now, where this gets tricky is imagine that, and the connection to spawn is that whenever I spawn a new future here, it just gets placed on a random worker. Random. This is a relatively recent change. It used to go to the same thread as you're spawning from, but it basically goes to a random worker every time you spawn. So I spawn this future, it gets placed, say, on worker 2. I guess we can number these. This is 1, 2. That's not. That's a 3. 3, 4. So every time we spawn a future, it gets placed on a random worker, and then what this might lead to is, imagine that we get really unlucky. Imagine that. Ooh, eraser. I'm into erasing things. This guy. This guy. Just like they finish all their futures. All of them finish relatively quickly, and so they have nothing to do. And so these have nothing to do. Meanwhile, this guy has lots of futures and is super busy. And this has like some, not terribly many, but a few. This seems problematic, right? Because it means that this thread is going to be really busy because they have all of this work to do, right? So they're really quite sad. So this CPU, whatever CPU is running this worker, is just like spinning at 100%. Meanwhile, we have these 2 CPUs over here that are idle. That seems stupid. And so this is why, if you recall back from here, it talks about how, where is it? This is a work stealing based thread pool. So what work stealing is this thread, when it goes in, let's pick another color.
Oh, come on, why is duping not working?
Right. No. This color. This color. So when this thread is on step 1, oh, it sees queue is empty. Well, that seems silly. So instead of just sort of looping on its own queue and waiting until it gets something random, right? So it could get one of these, but that might take a really long time. There might not be anything more coming. And so instead, what it's going to do is when it detects its queue is empty, then it's going to do like a special 1.3, which is try to steal. The way that works is it's going to look at the other, so in this step, it's going to look over here at this worker and go, ha, you have a ton of things in your queue that you're not doing anything with. How about I help you out? And it's going to steal some of the futures and pull them back to itself. And put it, basically, sorry, I guess this should go here, and it's going to stick those into its own queue. And then it's going to start working on it. And so now this work stealing means that we are, this work stealing means that now we're spreading the load. So if one thing is more busy than the others, then that load is now sort of moved. Of course, now we're in a slightly weird position where some of the futures that we stole might depend on wake-ups from here. Right? So some of the futures in here are waiting for notify to be issued from this thread. So there's an additional step here where if you steal something and then it has to wait for I/O or for a timer, then it gets put back sort of onto this queue. But it does mean that this thread 3, gets to help thread out 1 out, right? So the futures that it steals, it does a bunch of compute on it, polls on all of them, and then once they become not ready, it sort of returns them, but it returns them as not ready. So it has still done some work for 1. And similarly, 4 is going to do a similar kind of work stealing. We'll probably also steal from 1. And so now we're spreading the load out, and then we're still making sure that things end up sort of back where they were when things are settling down. And this is important because you could imagine that if thread 1 had to keep waking up thread 3 all the time, or sort of notify thread 3 all the time, you get a lot of communication, which is sad. So this is why we return the future to 1. But this is the basic idea of a work stealing thread pool, right? So in this setting, you basically have a bunch of threads that are all independently an executor and has all the stuff that they need, but they sort of cooperate to make sure that all of the workload gets spread out nicely. Does that setup make sense, or do you want me to talk more about these pools?
Cubing is so exhausting.
I know this is very random, but I started learning Python today. I will not spend time on the stream talking about Python bugs, because it's already pretty packed with things. But you should ask on like a Python IRC channel or something. So please don't take that here. But does this setup of futures and thread pools roughly make sense? Or do you want me to talk more about it before we move on? Makes sense to me. Great. I have 1 data point. I know that there's a lot of complication to this. Like there's a lot of I like pools. Nice. I know there are a lot of weird interacting components here, and it can be hard to follow the flow. I think going back to look at the recording after might help, and sort of go through it at your own pace and try to work it through in your head. Also, if you read, I assume it picks the queue with the most extra work.
Oh no.
Sort of. So you don't actually. So in this work stealing setup, if whenever a thread tries to steal, if it has to check with every other thread, that's also pretty slow. Imagine you have like a machine with 40 cores. You don't really want to have to talk to all the 40 cores to figure out which one to steal work from. So usually there's sort of an algorithm of you walk until you find some that seem to have a bunch of work, and then you take it. So you do it somewhat eagerly, so you don't end up interrupting everyone else. The only thing that might be worth mentioning is how blocking plays into this. I'll maybe get into blocking later. I will point out the issue though, which is imagine, and this is not just specific to the pools, but even for executors in general, imagine if you have some future that is just doing a lot of work. Like you call poll, and then it like computes all the digits of pi. So it just like takes forever to return. In fact, actually literally forever to return. Then now you're not going to make progress on any other futures. You're not going to check your timers. You're not going to check your reactor. And so it's just going to get stuck. That is problematic. Even in the stealing world, imagine that here this thread starts computing pi. Then now it's not even going to wake up the stolen futures. So it might have given some stuff away, but that's not going to make progress either. And you've basically now sort of lost a core, and anything that's stuck. So let's do like yellow. Imagine that there's some futures down here that no one ends up stealing because everyone else has their own work to do. These futures down here, no one is going to steal, but this thread is stuck just computing pi. Now, these futures, we're just never going to do anything with. Even if all the other threads are sitting idle, right? They're not going to steal it because they see that this queue is pretty short. Now there might be ways around this, but you can see how if a future takes a really long time, then this is problematic. And what Brian is mentioning here is there's a mechanism in Tokyo that's relatively new, where you can call Tokyo blocking, or technically it's in Tokyo executor, but blocking, which is you sort of mark the current pool thread as, hey, I'm doing a bunch of work, so steal everything I have. It basically sort of lets go of its own queue and says everyone else deal with it. So that I wanted to mention. There's another thing to mention, which is I mentioned how futures get returned to their original queue because otherwise they would have to get wake-ups from this other thread. There is a change that we want to make in Tokyo but haven't yet, which is how about instead of doing that, one color, we're running out of colors. Green. Green is not ideal for this, but let's use green. Fine. Here, no, not green. Pink. What if instead of doing that, we just sort of move the part of the reactor that's related to the futures we stole over here? That way we don't have to return the futures. We can just keep them here. It turns out that this pink stuff, we don't really know how to do yet, because it means that you have to move stuff from, we have sort of epoll running in thread 1, and we have epoll in thread 3, and it means that in this set to epoll, and this set to epoll, we have to take like the part of this epoll that is related to the thing we stole, we have to move it to this one, and Tokyo doesn't have a way to do this yet. That's something we're looking into how to add. Repeat why it's returning the future after it stole the future. Right, so that's a little bit what I got into here, but the reason is because otherwise we would have to do this, so if thread 3 steals the future from thread 1, then now thread 1, because it still has the resource, the thing that notifies that future, then now 3 can't make progress without 1 telling it what to do. And then you have to sort of bounce back and forth between the two with these notifies. Whereas instead what we're going to do is 3 is going to do the compute part, so do the poll, and then it's going to return it to 1 so that 1 can just do the wake-ups locally instead. I'd also like to learn more about Tokyo blocking. Yeah, so I think I got roughly into the idea of blocking. I don't want to go too much into detail, in part because the design there is still evolving. Like blocking doesn't work for current thread runtimes at the moment. Does reactor run in the same thread? Yes. So the reactor here. The reactor. So every thread in the pool also has a reactor. Remember, the reactor doesn't do reads or writes, right? Those are done in poll. All they do is epoll and notify. Up until, I can find out. Tokyo.
Was it like this or the other way around? Ah, like this, right?